In this example, we're investigating the question, is there a difference in the mean amount of time boys and girls aged 7 to 11 play sports each day? We're comparing two population means. We need to do a hypothesis test to be able to answer this question, but we're doing a hypothesis test with two different sample data. Our study collected data from 9 girls and 16 boys. The average number of hours playing sports per day for the girls is 2 hours, and for the boys it's 3.2 hours. Now, just looking at our sample data, you might be tempted to say, oh, I can answer this question. They're not the same. There is a difference. Boys spend more time playing sports. However, sample variability could be the explanation in this difference. So we'll wait to make our decision until we've performed the full hypothesis test. Just like with a single data set, our hypothesis test will start with two contradictory hypotheses. In the setup of our problem, we can see that one of our hypotheses is that the two means for the different populations is believed to be the same. The null hypothesis, then, is stating that the mean for girls is equal to the mean for boys. Our contradictory hypothesis would be the alternative hypothesis, and that simply says there is a difference. They are not equal to each other. So those are our two hypotheses. One is that the mean for each population is equal. The contradictory hypothesis is that they are not equal. We don't know if the girls spend more time or the boys do. We just are stating that it's not equal. This causes us to require a two-tailed test for this hypothesis test. In our two-tailed test, we're going to calculate a test statistic and then calculate the area, the p-value, to determine if we should reject or fail to reject our null hypothesis. This is just like the hypothesis tests we did on single sets of sample data. What's new here is how we calculate our test statistic. In this situation, we do not know the population standard deviation. So we have to use the test statistic formula that you see on the screen to be able to calculate a single test statistic that we can then use to calculate our p-value. We'll plug in our sample data information into our t-score formula. So first, starting by identifying the sample mean for girls as x1 bar and the sample mean for boys as x2 bar. Next, looking at our null hypothesis, which is stating that there's no difference between the population means, we know that the mean for girls minus the mean for boys would have to be 0. If they're equal to each other, then the difference between them would be 0. We'll plug in our standard deviations for the girls and for the boys, and we'll plug in our sample size for each sample group as well. Throwing that calculation into a calculator, we find our test statistic is approximately negative 3.14. Now, because we're using a t-score with the student t-distribution, we also need to calculate the degrees of freedom. This degrees of freedom formula was developed by Aspen Welsh. It's a formula that helps us approximate the most appropriate degrees of freedom based on our sample data. So again, we're just plugging in the values that we have from our sample. And when we throw this calculation into a calculator, we find our degrees of freedom is approximately 18.8466. With those two bits of information, we're ready to do a two-tailed test where we calculate the p-value from our test statistic and compare it to our significance level of 5%. Looking at a student's t-distribution with the degrees of freedom that matches our sample data, we can place our test statistic in the left tail. We're doing a two-tailed test, and our test statistic is left of center, so our area in the left tail will give us half of our p-value. If we double that, we find our p-value is approximately 0.005402. Pretty small p-value. In fact, it is smaller than our significance level of 5%. Same reason why we would reject a null hypothesis for a single sample hypothesis test. We're going to reject the null hypothesis for this hypothesis test with 2 sample data sets. Our p-value is small enough that we would say the results from these sample surveys are extreme enough to reject the original hypothesis, the null hypothesis, that the 2 population means are the same. We went through the calculation of the t-score test statistic and the degrees of freedom by hand by plugging our numbers into the calculator. However, there are pre-programmed calculators that can make this much simpler. For example, Statistics Kingdom is an online calculator that will allow you to do a hypothesis test for 2 population means with an unknown standard deviation. That's exactly the problem we're working on. We identified that we were looking at a 2-tail test, so we will use the drop-down for 2 tails. So the very first drop-down is the type of test. Next, you will enter in the significance level alpha of 5%. We're going to leave the effect, effect type, effect size, and outliers as their preset. So we don't need to change those next 4 entry points. Leave them as they are. And then the difference. In this case, we're testing whether there is a difference or there is not. If there's not a difference, then we would say the difference between the 2 population means is 0. If there was a stated difference, if the claim was that the difference between means is 2, then we would plug the difference of 2 in here, but we're going to use 0 for this problem. Next, we're going to put our data in, and we're going to do just our sample statistics. We have 2 groups, boys and girls, and we have the average and sample size and standard deviation for each group. So for girls, we plug in sample average of 2, sample size of 9, standard deviation 0.866. For boys, we plug in sample average of 3.2, sample size 16, sample standard deviation of 1. Then we click Calculate, and the online calculator produces the image you see on the right, which is the summary of the hypothesis test. Now, in the heading, you can read the degree of freedom calculation. It's the same number we got when we did this by hand on our calculators, 18.8466. It does jump right to the end conclusion. Our hypothesis is going to be rejected, just like we determined by doing the hypothesis testing by hand. The calculator takes in the information you give it and immediately produces the decision, reject the null hypothesis. And then it kind of writes a conclusion for you. The average of girls' population is considered to be not equal to the average of boys' population. Notice that the computer has no idea that we're talking about the number of hours spent playing sports each day. They just know that we're talking about girls versus boys because of the way that I named the groups. This is also going to give you your p-value and your t-score test statistic. Now technically, we don't need those 2 things just to make our conclusion. The calculator has already told us that we're rejecting the null hypothesis. But remember, the p-value can tell us how confident we should be in our conclusion. If our p-value is very close to our significance level, then we're not very confident about whether we've chosen to reject or fail to reject. If the p-value is pretty different than our significance level, which in this case it is, it's an order of magnitude different, we can be quite confident in our conclusion that we've made. And then lastly, the test statistic. It's nice to know what the test statistic is. That way we can draw a sketch to help us understand how extreme our sample data is, how far into the tail have we gone. Also, it would allow us to perform this test using the critical regions. rather than the p-value method. So we could compare our test statistic to the critical t-score that we would have for a significance level of 5%. So the Statistics Kingdom hypothesis testing calculator for 2 population means with unknown standard deviations gives us all of the information we need to be able to make a conclusion for our hypothesis test.